for joining. Thank you very much for joining us today. For your information, this seminar is being recorded, as you just heard, and will be made available on RemPlex website. And at this point, I would like to ask everyone to mute your microphone during the presentation. All right, my name is Nick Chafoku. I am a scientist here at PNNL, and I'm also serving as one of the RemPlex deputy directors. And I'm moderating today's seminar together with my colleague, Karen Smith, who is the RemPlex deputy director for operations. For this specific seminar, I would like to actually acknowledge the help of Kelly McIntosh and Melissa Perdue. Both they are here at PNNL in putting together and advertising this seminar. And as you probably know, this seminar is brought to you by RemPlex, that is the Center for the Remediation of Complex Sites, which basically is a forum for sharing knowledge and promoting collaborations in the realm of environmental remediation. If you are interested in listening to the recordings of the previous seminars, please feel free to go to the RemPlex website, and a link will be provided in the chat as well. All right, now turning to today's seminar, our topic is the end-state-driven performance-based management of the pump and treat remedies. We have two outstanding speakers today. They happen to be here at PNNL, Inci Demirkanli and Xuehang Song. They are both in the subsurface group here at PNNL. And Inci is also serving as one of the deputy directors of the RemPlex. The theme today, or the focus today, is on the pump and treat remedies. It's a topic that is near and dear to many of us here at PNNL and worldwide. It's a technology that has been used quite often in many contaminated sites, but there are some benefits and challenges employing these remedial methods. And for us to hear today, we have Inci and Xuehang to talk about all these benefits and challenges employing this remedial method. Without any further delay, I will actually like to turn the microphone to Inci. She is going to start us today with the seminar. Inci, the floor is all yours.
Thank you, Nick. I'll share my version of the slides here real quick. And we'll go from there. So I hope everybody is able to see my slides.
Yes.
Thanks, Nick, for the introduction, and thanks everybody for joining the seminar today. Xuehang and I are very excited to go through this presentation to talk a little bit about our work related to pump and treat management strategies, optimization strategies, particularly performance-based optimization with end-driven focus. So we structured our presentation in three parts. In the first part, we want to sort of focus on some background information for those of you who might not be very familiar with pump and treat systems. We will provide very brief information about the description and the objectives of these remedies for addressing groundwater contamination. And then we will very quickly start talking about the concept of performance-based optimization for the pump and treat remedies and what we mean by that. And when we talk about optimization, obviously it is a computational approach. So we will talk about different computational approaches and the approach that we selected for the development of our pre-screening tool. We developed a framework to allow us to do some optimization strategy development type of evaluations for pump and treat remedies. So we will introduce that framework in this part as well. And in the second part, we want to focus a little bit on how this framework and the pre-screening tool could be applied to an actual pump and treat system. And lucky enough for us, we have a pump and treat system here at Hanford, and we are going to use that as a demonstration case just for the demonstration purposes. And we will also present some scenario evaluation approaches that we can utilize the tool for, the pre-screening tool for. And finally, in the third part, this is going to be very brief, but we didn't want to miss it because we are also doing a lot of work here at PNNL related to deep learning approaches. And we have developed different methodologies or capabilities that actually are targeting to enhance our pre-screening framework. And one example we will talk briefly about is the deep learning methodology that we applied for better predicting well performance predictions, estimations. And in the second example, we will focus a little bit more on the expediting or reducing the computational burden by using deep learning approaches within the framework of pre-screening tool. So with that, I'll just kick this off with the first part and very brief background information about pump and treat remedies. These are widely used remedies, as Nick was just alluding to earlier, for addressing groundwater contamination. And they can provide hydraulic containment of contaminated groundwater and also allow us to be able to extract that contaminated groundwater for treatment purposes, above ground ex situ treatment purposes. So they typically have three main components within the system. The first one is the extraction well network. Obviously, we have to have a network of wells that are extracting this contaminated groundwater from the subsurface. And on the right-hand side, you see a picture of an extraction well head, actually, with the instrumentation. And then extracted groundwater is transferred to an above-ground treatment facility. And based on the contaminants that we have in the groundwater, certain treatment processes are utilized in this unit to remove the contaminants from the groundwater. And finally, the last component of the pump and treat is the disposal system. So this treated clean groundwater would have to be disposed of. And typically, especially in large pump and treat systems, this water is injected back into the subsurface to enhance the hydraulic contamination of the containment of the contaminated groundwater. So initial designs of the pump and treat systems are typically intended to address the immediate risk associated with the contaminated groundwater. So these designs are typically large scale, intended to contain the contaminated groundwater, and they focus on bulk treatment with the goals like volumetric pumping, a total amount of pumped water in a year, for example. At the very beginning, this is an effective strategy and it addresses our risks immediately, but as the time goes on, this might not be the most optimal management strategy or design strategy for the pump and treat for most effectively removing the contaminant mass from the subsurface and achieving the targeted end state in the most efficient amount of time. So, and you will see later on, we will discuss how these different goals for the pump and treat and adjustments could be changing over the lifetime of an operation. And we typically see if there's no significant optimization efforts, what we typically see with the pump and treat operations is that the performance could be diminished due to some complex factors. And these factors may include the heterogeneity. This could be subsurface heterogeneity or contaminant heterogeneity, distribution heterogeneity in the subsurface. It could be related to large scale or dilute plumes. And these type of plumes would require many pore volume flushes in order to get them sort of move towards an extraction well network. So it might take a long time and the performance could be diminishing as the time goes on. Another complexing factor here is the presence of source zone or diffusion limited mass transfer zones in the subsurface. And these typically contribute to the contamination in the groundwater. So as we pump, we would get more contamination coming into the groundwater from these type of zones. And finally, recalcitrant contaminants or competing contaminants that might require different kind of pumping strategies might also delay achieving the end state that we target with these systems. So what we propose here with this idea of performance-based optimization is that the optimization could be conducted periodically for these systems to maintain, or if necessary, increase the contaminant removal effectiveness and efficiency throughout the remedy lifetime. And in our approach, the pre-screening tool approach, we specifically focus on well network extraction, well network optimization, and the capacity evaluations. But the optimization of pump and treat remedy could be more comprehensive than that. You could take a look at the monitoring well network optimization or the treatment processes optimization and such. In the right-hand side, you see on the slide, you see a flow diagram, which kind of depicts how a periodic performance-based optimization could be integrated into the lifetime of pump and treat remedy management. We start with a design state and the initiation of the pump and treat remedy. And as we collect data about the remedy through continuous performance monitoring and conduct our performance evaluations, we can understand how we can improve this remedy or its mass removal efficiency, mass recovery efficiency. All of that information, the performance assessments, feeds into our site conceptual model, CSMs. And there could be some additional information activities at the site, like additional site characterization and such, that could still feed into these CSM updates. And this updated CSM then is moved into or fed into these computational optimization evaluations for well network adjustments and network effectiveness. So performance-based optimization has been the topic of a recent guidance document published by ITRC, Interstate Technology Regulatory Council. They published this guidance document in 2023, and the guidance document is very comprehensive. It does talk about the performance-based optimization approaches in a more comprehensive sense. For example, it addresses the monitoring well network or the process optimization needs and such. It talks about the life cycle approach for the pump and treat systems. It also provides some information about the potential cost benefits of performance-based optimization approach. And we took that information and we kind of wanted to depict how a performance-based optimization might be beneficial from the life cycle perspective if it focuses on well network and capacity type of evaluations. And the graphics on the right-hand side here kind of conceptually depicts that idea and give you a comparison between no optimization and performance-based optimization applied to a pump and treat system and potential benefits of it. So at the top graphic, what you see here is that we have a cost structure or the cost profile for conceptually a cost profile for a pump and treat operation. At the very beginning, we have the remedy design and initial cost, construction cost, and following that, when the pump and treats comes online, we have this pretty constant O&M cost throughout the lifetime of the operation. Just speaking conceptually here. And once at the end state, targeted end state is achieved, this pump and treat, the pumping portion of the remedy, pump and treat portion of the remedy, then can be stopped and the remedy could be moved towards more passive strategies like M&A, monitored natural attenuation, until the end of the remedy is achieved. In that case, the constant cost it could be a reasonable expectation because we have no optimization in this or significant optimization in this system, and we have no significant changes to the treatment capacity or the well network. If we apply a performance-based optimization approach to a pump and treat remedy, you can take a look at the graphic on the bottom. Now, we still have this initial cost of remedy design and initial construction, but now you can see that our cost could be fluctuating year to year or every other year, whatever the frequency of optimization evaluations that we have for that system. And some years we might incur higher costs because we might identify a need to increase the capacity or add new extraction wells and take off certain extraction wells from the system. So these fluctuations might cause some increase in cost in certain years. But the goal is that the optimization strategy that we develop and evaluate and try to implement would have to have a focus on the end state. So it has to be driven by achieving the certain end state in the most effective and efficient way. So if that optimization strategy can bring the pumping time to a shorter amount of time, as you can see on the right-hand side of the graphic, bottom graphic with the yellow area, then it can help us gain a larger benefit, net benefit in the life cycle cost evaluation for these systems. So our idea was to be able to look at these type of scenario evaluations and state-driven scenario evaluations with a computational framework that utilizes formal optimization algorithms. So when we talk about formal optimization for a pump and treat, this is computationally very burdensome approach. So you would have to have a fate and transport model of your system, pump and treat system, whichever subsurface domain it is operating. And that fate and transport model would have to be coupled to a formal optimization algorithm. And then we are talking about running thousands of simulations. And this is computationally very burdensome and very difficult to do many scenario evaluations. So in our approach for the pre-screening tool, we decided to reduce the complexity of the fate and transport model that depicts the pump and treat system behavior. And we achieve that reduced complexity in different ways, and you'll see an example later when we are applying this tool to 200 West pump and treat operations. We can reduce the domain, we can reduce the certain complexities of the subsurface geology and such. We can take different approaches to this reduced complexity fate and transport model. But by reducing the complexity of the fate and transport model, we are able to increase the efficiency, computational efficiency of the framework when we are running this tool. And we are coupling this reduced order model, the reduced complexity model, to formal optimization algorithms still. And our goal here is to be able to easily provide different goals, different scenarios, different range of assumptions, and be able to get a comparative assessment of these different strategies and their benefits at the end. And once we are able to narrow down the potentially successful strategies, then we can take those into the actual decision-making fate and transport models and further evaluate and further improve those strategies in that environment. But this pre-screening tool is basically for scenario evaluation and comparative assessment of those scenarios. So just a little bit more information about the pre-screening tool and the framework, and we just wanted to show you how it works. It basically has these three main components in our framework, and we just talked about the reduced complexity fate and transport model, which you see on the bottom left corner of this framework depiction. So that represents our reduced complexity fate and transport model. This is where we run the models to understand the system behavior, pump and treat system performance and such. And then at the top, we have the optimization component. This is where we are able to input different scenarios, different goals, different constraints, and different assumptions. And so we can do these comparative assessments between scenarios. This is the scenario setting component of the framework. And on the right-hand side, what you see is the evolutionary algorithm that we use for finding the optimal solution to our problem. So evolutionary algorithm is a stochastic approach for both solving the single objective or multi-objective problems. Here, primarily, we use a single objective problem, but we are moving towards multi-objective later. So what it does is that it takes our setting, the model domain and the optimization setting information, and it runs many thousands of realizations. And through these thousands of realizations, it approaches to an optimal solution at the end based on the goals and the constraints that we set up. So for the part 2, what we would like to show you is how this framework and idea of pre-screening scenarios, optimization scenarios, might work for an actual pump and treat systems. So as I mentioned, we would like to use our 200 West pump and treat system here at Hanford for this demonstration purposes. And for those of you who are not very familiar with the Hanford site, this site is located in Washington State in the United States, and it was historically used for supporting the Manhattan Project for plutonium production. So there was decades of production operations at the site, resulting in significant groundwater contamination, especially in the area that we call Central Plateau at the middle of the Hanford site, as you can see in this map. And here, historically, the chemical separation operations and waste management activities occurred, and they resulted in significant contamination in the groundwater. And we have our 200 West pump and treat system is located in the Central Plateau, as you can see, to address some of those groundwater contamination and groundwater plumes. This pump and treat has been operating since 2012, and according to the record of decision that established the pump and treat, it is supposed to be pumping for 25 years. And it's addressing the groundwater plumes for carbon tetrachloride, technetium, uranium, chromium, and nitrate originally, but currently nitrate treatment is suspended under an optimization study to evaluate transitioning to monitored natural attenuation. And the capacity of the pump and treat system is about 2,500 GPM, gallons per minute, and it has about 38 existing extraction wells and 30 existing injection wells. So just a little bit more information about this pump and treat system. And I mentioned the optimization study that is currently ongoing at the site. One of the plumes that the system is addressing is the carbon tetrachloride plume. And this is a very large scale distributed plume in the Central Plateau. And we have some technical challenges associated with carbon tetrachloride. We know that the degradation rate for this compound is way lower than what we originally expected during the issuance of the record of decision. And we also know after the performance evaluations, periodic performance evaluations since 2012, that there is now more contaminant mass, carbon tetrachloride contaminant mass in the system than originally assumed. And we also have some diminishing performance at certain locations in the Central Plateau for the pump and treat for carbon tetrachloride extraction. So for addressing some of those challenges, the site initiated an optimization study here, focusing on potentially increasing carbon tetrachloride removal and treatment here. And as I also mentioned, that nitrate treatment is also suspended during this period in order to evaluate its transitioning to monitored natural attenuation. So with this background information about the pump and treat system, we will start talking a little bit about how we are applying our pre-screening tool and methodology to this pump and treat system. And I'll hand it over to Xuehang, my colleague Xuehang here. Xuehang.
Yeah, thank you, Inci. Can you hear me?
Yes.
Yeah, please feel free to jump in if I miss any key points as we are co-presenting this. So on this slides, we are showing the reduced complexity model used for the 200 watts pumping and treat. So on this slides, on the left side is Hanford contractors flow and transport model, which covers the central plateau area all the way to the Columbia River, for all the area covered by the mesh. So this is often referred to as a plateau to river model. So on the right side is a smaller, reduced complexity model extracted from the larger plateau to river model. So the reduced complexity model focuses only on the MnCOC carbon tetrachloride. Well, we keep the same discretization of the P2R model for consistency. We do simplify the boundary conditions, and we focus on the centered pumping and treat well field. And in this model, there are 4 major combined geologic units. As you can see, the 7 layers here on the top is the most permeable Hanford and Cold Creek units. Below that, there are 4 layers of Ringgold Taylor Flat and Ringgold E units, where most of the containment is in this layer. Below that, there is a least permeable Ringgold lower mud layer. It's very thin, but very low permeable. And the very bottom is the Ringgold A formation, and with the permeability in between the Ringgold E and the Ringgold lower mud. So for all the carbon tetrachloride, they are staying in the other 6 Ringgold layers. And please, next slide. And in this slides, what we are showing here is the initial carbon tech concentration in the reduced complexity model. We map that from the larger P2R model. So the background of this image is still showing the 7 layers. It's partially transparent, probably cannot see it very clear. But in the center of the domain, the plume used in the simulation. So the color here, the warm color means high concentration area, and the cold color means a low concentration. And please note this plot is plotted in a log scale. And then on the right side are the extraction and injection wells we use in the model simulation. The extraction wells, which are the pink color here, these are in the center of the domain, and the injection wells are in the surrounding area. So the main role of the injection well is to provide hydraulic containment of the containments. Next, please. So I think let's revisit the pre-screen optimization framework. Now, where recall, we identify 3 major building blocks: the optimization components, the model, and the optimizer. So in the previous 2 slides, we will talk about the model. And now we have to think about the optimization scenario and objectives and constraints to evaluate. And we need to, based on that, to formulate the optimization problem. And next slide. Thank you. So in this demonstration, after discussion with various stakeholders, and we focus on 2 scenarios for evaluation on top of a baseline case. So the baseline case here is showing on very top. We are assuming that we keep a fixed pumping capacity, and then we keep a static well network, means we don't change the well network. We run the network on all the way to the end of fiscal year 2037. And scenario 1 is we keep the same pumping capacity at the baseline case, but at the same time, we allow our algorithm to change the well network, to including adding new wells and turn off old wells. And on top of that, the scenario 2, starting from 2026, it begin to increase the total pumping capacity, which means in this case, we are allowed to install more extraction wells. And so these are the 2 scenarios and the baseline case. For these simulations, the major end state performance criteria we look at is the baseline 95 percentile concentration level in the end of fiscal year 2037. For each of these scenarios, we run the optimization simulation with two different optimization goals. The first goal is to minimize active time frame, which is try to achieve the same baseline concentration level as soon as possible. And for the second goal, we just try to maximize the carbon tech mass recovery. Next slide. So with the optimization objective and constraints in mind, we start to develop a specific parameterization method to simplify our optimization problem. So why we need a specific parameterization method? Just consider this, like we already have 38 wells in the well field, and we are going to install up to 20 or 30 more wells. We need to decide when and where to install these wells. This creates a problem with very high dimension. I mean, just think about the different combinations or locations at the timing. So we have to find a suitable parameterization approach to help to simplify this problem, and at the same time without too much compromise on the optimal solution. So skipping all the mathematical details, the fundamental parameterization rule here is assume we want to run the well replacement with the maximum number of active wells based on the total capacity of the treatment plants. For that, we assume each well has a fixed pumping period and a fixed pumping rate. When a new well is installed, it will replace an old well. And on the right side of the slides, these are examples of the well installation schedules. Recall that we are using an evolutionary-based optimization algorithm, which requires us to build up an initial population or generation of well installation schedules and locations. The algorithm can then, based on the outcome of this first generation, and continue to improve or change the well net installation timing and location to achieve better optimization goals. So on these slides, the three examples of our well installation schedules from left to the right, the orange color represents existing wells, and the red color represents the new wells being installed. As you can see, when we randomly generated these installation schedules, they have very different numbers of new wells. The one on the left has a lot of new wells, which indicated by the red color. So the x-axis of this image is the pumping duration, and the y-axis is the name of the wells. So a well can be turned on and run for a certain period of time, then it's turned off. So for each generation of our evolution algorithm, we have 1,000 such schedules. Please, next slide. So at the same, in addition to the schedules, at the same time, we need to find the location of the new wells. So on the left side, we are showing examples of new well locations. Again, these numbers it varies, and we go from one realization to another realization. So these are 9 different realizations, and as you can see, there are polygon around this red dots around this new well. These are the injection ring, defined by the injection wells. So what we did here is we use a concentration weighted sampling to create this initial well locations. That is to say, where the carbon tech concentration is higher, it's more likely be choose as a location for a new well in our algorithm. So we don't waste too much time on the low concentration area. And on the right side, this is a probability map showing which location is more likely to have a new well. And the red color means a higher probability, and the blue color means it's a lower probability. And you can see this black hole here, the black area, this is where the field building is, and where the existing well is. No, we don't want to restore stuff on top of that. And we also have a algorithm that we select the new well recursively to make sure we don't put new wells on top of each other. And in the next slide. Okay, so moving to the results part. So this slide provide a very high level summary of the optimization outcome of the two different scenarios. So 3400 GPM and 4500 GPM for the first goal, the minimizing the active pumping frame. So on the right side of the figure, the x-axis is the number of the new wells being installed for different simulations, and the y-axis represents the year that the simulation reach the baseline concentration level. So there are two cluster of results, so one for each scenario. What I'm plotting here is the final generation of the from the evolution algorithm. So each of these two clusters, each dot of these two clusters represent a single realization. So on the top left of this entire figure is the result is from for the scenario 1, and the black circled dots on the very top left represent the baseline case. Recall, like in the baseline case, we installed 0 new wells, and they ran all the way to 2000 to the end of fiscal year 2037. And the optimal solution for this scenario is highlighted as the red circle, which can achieve the same concentration level as the baseline case 2 years early. And consider our total active pumping period is about 8% reduction on the active pumping time frame. So we also draw an additional line here, the dashed line here. It's really showing how the year of time reduction change with the number of new well being installed. And the results from the scenario 2 are shown on the bottom right. And it's clear that due to the increased pumping capacity, we can install a lot of more wells, which actually significantly reduce cleanup time by about 24% by 6 years. And this is for the results for the optimization goal of like reducing the time frame. And now let's move to the next slide. So this is a summary of the second goal. So for this one, we have a similar plot. The only difference is we changed the y-axis to the mass recovery. And as we can see, the difference between these two clusters, between these two different scenarios, became smaller compared to the previous slides. As the mass recovery was limited by the continuous aquifer drawdown. Since our main end-state criteria is 95 percentile concentration, although we don't optimize for this case, we still look at the results for this criteria. So for the cluster 1, for the scenario 1, what it can achieve on this criteria is 1 year reduction, about like 4 times in the left circle. And then for the scenario 2, it's 5 years. It's 20% reduction. It's less optimal if you just look at the end-state criteria.
So if I can jump in here,
Sure.
Xuehang, just to
Please.
pause, because these are pretty important plots demonstrating how different optimization goals can affect the optimization strategy development. And the goal, the first goal, we were trying to minimize the pumping time, and that was explicitly inputted into our framework. And so all the realizations were run based on achieving the minimum pumping time period. And here, and typically when we are looking at pump and treat operations, we also think about maximizing the mass recovery, contaminant mass recovery, and we think that it is almost equal to reducing the pumping time frame. But what we see here, when we set up our goal as maximizing the mass recovery, it still provides an improved solution compared to the baseline. We are able to bring down our pumping period 4% or 20% below than what we have in the baseline, but it does not achieve the same success in terms of the pumping time frame as setting that goal as minimizing pumping time frame. So I think it is an important distinction, because with the goals and the constraints that we set for formal algorithms, the optimization algorithms will help us define or develop different kind of strategies. And with this type of pre-screening tool, we are able to assess the impacts of different goals or different constraints and different strategies in the end period or the life cycle assessment for a pumping tree. So I'll just move to the next slide now, Xuehang.
Yeah, thank you, Inci. Yeah, yeah.
Sorry.
Yeah, thank you for your inputs. And yeah, I think your point, it became more evidence when we move to these slides. You know, if you look at the parental front of this analysis of these results. So for this figure plotted two objective values altogether, and the x-axis is the year that we reached the baseline concentration, and the y-axis is the total mass recovery. So if we pay attention to the parental front points which are in the red circles, they are showing that on these fronts that the improvement in one objectives actually can cause a degradation in the other. For example, if we move along this parental front, if we want to keep decreasing the year that reach the baseline concentration, like reducing the time frame, then we will have to decrease the mass recovery. So this showing at some point these two objectives start to competing, and then this slope of this parental front actually showing the rate of this change. And move to the next slide. Yeah, so this is another comparison among all these 4 different set of simulation. So these are the new well locations proposed, and on the top 2 rows, the top 2 represent the results from the first goal, which is to reduce the pumping time frame. And the bottom row represent the second goal, which is to maximize the mass recovery. And on the left of this 4 subplot, on the left is the scenario 1, with smaller treating capacity. On the right, the scenario 2 is a larger treating capacity. So I think it's pretty clear that different optimization objectives result different strategies for selecting new well locations. So on the top ones, when we try to minimize cleanup time, the new wells are placed mostly in high concentration zones. Can you move back? Zones, and it really want to reduce the concentration, to beat the baseline case. But for the mass recovery, wells are spread out and to have a better coverage, especially spatial coverage, especially as the concentration decreased. And this shows that the well placement strategy should change with our objectives. And can we to exercise? So in the following 2 slides, we will just show an example that what's the final outcome of this optimization well isolation schedules and well locations for these demonstration cases. So for the scenario 1, I mean the well isolation schedules is shown on the left. There are 7 new wells being installed at a different year, and on the right part, the first image showing where the 7 wells are, and we also have a subplot showing in which year a new well is being installed in where, on where. And then in the next slides is just the same plot, but for the 4,500 GPM case. And Then, can you move to the next slide? So as the last slides for this demonstration part, the part 2, we are showing the animation of how the plume migration change in response to a new well being installed. So on the left side, we know the red cylinder is the extraction wells, and the blue cylinder is the extraction wells, and the pink one are the new wells, and the background are the plume. And on the right side, the blue color are the baseline pumping rate, and the solid backline are the new extraction rate for the 4,500 GPM case. And this is the massive recovery. And the dash green line are the extraction rate. And the animated red line is mass recovery from optimal case. And then you can see how with the new wells being installed, the mass recovery improved over time. Inci, can you move to the next slide? So, okay, so coming to the last part, the third part of this presentation, as you can see from the previous demonstration, we rely on a reduced complexity model for the flow and transport modeling. And we have to make some compromise during the optimization, such we have a fixed pumping rate for a certain pumping duration. If you want to consider dynamic pumping and multiple pumping duration for a single well, it complicates the problem, and it will greatly increase the number of the parameters. In the following, in this section, I'm introducing the deep learning methods we have been developing, helping to solve this problem. So on these slides, we are showing the first one. This one we call it well performance index tool. This is it's bothering you. Sorry. And this is data-driven classification model. Recall that we have more than 30 extraction wells in the field, and it started to operate from 2012. And we have a rough idea of their surrounding plume distribution, the geology information, and their hydraulic conductivity estimations. At the same time, we have their historical data for the past 12 years. So what we did here is we use a convolutional neural net to build a classification model between these plume hydrogeology features surrounding each well and their pumping performance, indicated by the mass recovery. And what we get is a prediction tool that can be used to estimate and in any future locations what will be the performance if we install a new well there. So you can move to the next slide now. Thank you. And the left side of this image shows this is the results for the performance index tool. And the left side of this image, it shows a projection data set. It indicates what the performance of a new well might look like in the next 5 years. So the green color here represents locations that are more likely to have high mass recovery. The orange color represents medium performance, and the red color represents locations likely to have low performance wells. And notice this is a probability map. So higher probability means we have stronger confidence on these projections. And on the right side, we can see a training and validation during the deep learning model training, which is about 80 or 90% accuracy during training. So what this deep learning application can do, it can be used to rebalance the pumping rate of existing wells. For example, we can give higher pumping rate if the aquifer allows that. We can give the higher pumping rate and lower the pumping rate for low performance well based on the future projection. And we can also use that to reduce the number of candidate locations for the optimization simulation. And it can provide a good performance estimation compared to just based on the pixel values on the concentration map. And it can also be integrated to flow and transport model. to provide on-the-fly kind of optimization or pumping rate, but it will take some coding efforts for that. This work has been published in the Journal of Hydrology last year. And can I move to the next slide? Yeah, I already talked about these points. Thank you. So in this slide, this is the second deep learning model we developed. So this is more like a surrogate model we developed for plume prediction. So this model uses a UNet convolutional neural net architecture. What it do is it take previous year's plume distribution and a well drawdown map, and then to project what the next year's plume distribution will look like, will be. And I'm not talking too much about the technical details of the UNet. It's a popular method for image segmentation. And it has a down sampling on the left branch and up sampling on the right side approach that's used to extract shape features and different scale, and then combine them to create a new image. And on this figure, the right is the training and validation of this deep learning model. And you can move to the next slide. So on this one, we are showing is a example of the prediction from the UNet model. So is that a question? So so for this one, each column of this plots showing the different model layers, like the Ringgold E, Ringgold lower mod, and Ringgold A layers. And that's for the different column. And the first row is the groundwater head calculated using team equation, using well locations at the rate in certain year. And then the second row showing the plume from a given year, and we are try to predict the target for the next year. The plume is the next year, which is the third row. And the fourth row here is showing the plume change. The fourth row here is showing the plume prediction, what we get from the UNet model. And the fifth row here is actually showing the plume change over this year. So, and that's the kind of migration on top of pumping. What will change? It will change the plume. And the very bottom is our prediction error. So I have to highlight that when we plot this prediction error, we actually change the scale of this plot, compared to the original plume distribution. So for this one, the bound is 3.4 microgram per liter, which is our cleanup standard. And on the top ones, they are about 1500. So you can see the prediction actually is pretty good for the plume distribution. And I think most importantly, by using this model, we can predict like 1,000 times faster compared to the detailed flow and transport model. Allow us at least partially replace some of the work of the numerical model to accelerate the evolution algorithm. And actually, we can move to the next slides. So in conclusion, the pumping trade optimization pre-screen tool allows us to evaluate how our system behavior under different scenarios. Now, it's provide a way to propose active management strategies that can help us achieve our optimization goals. And the second, and we have demonstrated that the formal optimization of a pumping trade well network in the Torrential West. And this involves considering the size of the well network, the location of the wells, and the pumping operation strategies to meet our optimization goals, our end state goals. So this results promoting, and we can see the potential to reduce the cleanup time frame and increase the mass recovery. And it's also important to know that optimal outcome can vary depends on the optimization objectives and the constraints. For instance, if we select maximum mass recovery and the goal, it might not necessarily lead to the shortest cleanup time frame. And lastly, the use of the deep learning approach, it can significantly enhance the computational application of the framework and can improve our efficiency. Yes.
Thank you, Xuehang. So this concludes our presentation for this seminar, and we are happy to take any questions you might have.
Well, thank you, everyone. This is Karen. Thank you both, Inci and Xuehang, for the presentation. We have a couple of questions that are coming into us. I'm going to start with one. It's from our colleague, Chris Johnson, here at PNNL. It looked like the new wells in your example were more on the edges of the plume versus in the plume core, which seems counterintuitive for mass extraction. What are your thoughts on this? Were there other results with more new wells located in the plume core?
So I'll go back to the slide that I think Chris is referring to. Sorry. So is this the one, Chris, or is this the
Yeah,
one?
that slide in the previous one, I think, or yeah,
Previous one.
those slides, yeah.
Yeah, I think the strategy here is to this is the cleanup time frame reduction. Is that right, Xuehang? And so we would have our initial new extraction wells at the higher concentration areas at the very beginning. But then as time goes, the concentrations are reducing. And I don't see the concentration, the legend here, but I would assume that the periphery of the plume is very similar to the center of the plume here in terms of the concentrations. And the location also depends upon the available grids for the well location, well placement as well. So we in one of our constraints is that to avoid hydraulic interference between pumping wells, we set up 100 or 150 meter sort of a boundary around the pumping wells in order to consider the other locations for a new well.
That's great, Inci. We do have a question in the chat, and Walter actually wrote, do you have requirements on the pump system so you don't add contamination to fluids brought up to treat them? For example, sanitary or NSF pump specifications.
We don't necessarily have specific requirements on the pump systems. Our framework primarily evaluates the pumping locations and the time frame in the domain. So I'm not so sure what the reference is for adding contamination to the fluids that are brought up to treat.
Yeah.
But again, for the framework that we have, pre-screening framework, we are specifically focusing on well network adjustment. So the location and the timing of the new extraction wells and how those strategies might impact achieving a certain end state, as opposed to optimizing specific processes that might actually optimize the treatment that is happening in the treatment facility, right? There are research to consider different type of treatment units or processes that can optimize your capacity at the above ground facility. But this framework that we are talking about specifically focuses on subsurface contamination extraction and the well network and capacity evaluation, total capacity evaluation from the perspective of well network needs.
Yeah,
Yeah.
no, that's good answer, Chi. Yeah, I think Walter is going to be happy. If there is any follow-up question, please feel free to add it in the chat. I
So
do have a question. Oh,
Nick.
okay, go ahead.
I was just gonna jump in. I think Indy's just exactly right, that the work here is really about the extraction and the well network. And what Walter's asking about is more of an operational thing,
Mhm.
choosing the right materials and right pumps.
Right.
So not quite the focus of what Indy's doing.
Right, but I can actually refer back to the ITRC guidance again. ITRC guidance is way more comprehensive than what we are covering with our pre-screening tool. And that has a lot of considerations for process optimization and treatment optimization as well. So there might be some good information about pump specifics and such there.
Yeah, thanks. Thanks, Inci, and thanks, Chris, for clarifying that question. Inci, I saw a slide there that you mentioned a couple of contaminants that are present at Hanford. And I did not see iodine for some reasons. And the question is that, is iodine part of the pump and treat system? And you guys are thinking of treating iodine as well?
So no, so iodine is not currently required to be treated, although we are hydraulically, well, the site is hydraulically containing iodine per requirements. And there has been some technical evaluations of iodine technologies for treatment, and I believe none has been identified as feasible for treating iodine directly. So
All
iodine,
right, thank you.
yeah.
Yeah, I was wondering because we always say that, okay, well, iodine is one of the major contaminants and et cetera, but I did not see that there. And I do have another question, Karen, if
You go ahead, and I've got another one. There's another two that have come through in chat, but you go with your next one.
yeah, I was wondering, this is again a general question, can this framework be applied to other, I mean, the application here at Hanford is pretty obvious. I mean, it's pretty great, it's working great so far, can be applied in other areas as well. Do you see any issues with that?
Yeah, other pump and treat. Xuehang, do you want to take that? I can also provide.
Yeah, I think so first, like in general, this framework can be applied to other sites, but I do think there will be some customization, because every site is different and you need some special design. But another thing is that Hanford site probably is one of the most complex site, and if you apply to other sites, what we need to do is maybe make it even simpler.
I would think so as well. I think the capacity evaluations and the system with multiple contaminants, we are kind of
Right.
applying plans to apply our framework to multiple contaminant optimization at the same time. Other sites might provide simpler cases, although they might have their own complexities. And I would say, a pump and treat system would probably have a patent transfer model developed already and some level of data. It could be developing the well index tool, which is the deep learning tool predicting the well performance, could be applicable anywhere with pump and treat data, historical pump and treat data. So that would be very straightforward. And also applying the pre-screening framework could be very applicable to if there's a fate and transport model. And one thing that we didn't get into in our talk here, didn't want to complicate the story more, but uncertainty evaluations are very doable with type of approach as well, pre-screening approach, because we can reduce our complexity for the fate and transport model slightly differently to reflect the certain uncertainties that we might have in a system and conduct certain scenario evaluations with that uncertainty addressed. So you can see how your pump and treat might behave to achieve an end state in the realm of those uncertainties, how those uncertainties impact the pumping lifetime, for example. So those type of evaluations, I think, would be very useful for a lot of pump and treat systems.
No, that's great, Inci. I mean, yeah, that was a great answer. I mean, I really liked it. I do have one final, Karen, sorry. It's
Go ahead. That's
when
fine.
you guys do the when you guys do the work that you part of the work that you presented, the optimization and everything else, which was outstanding, by the way. Do you guys consider combining the pump and treat with other technology like water flushing? Inci, you probably are familiar, and Xuehang, you probably are familiar as well. Do you consider those combining technologies as well?
So that's an interesting question. So in the modeling realm, you can do a lot of different things, right? If you are applying another in situ technology for your contaminated site, you might try to include that in your model or its impact in the model somewhat, and then run your scenario evaluation. So that's actually another very interesting idea there. You know, if you have a site, it doesn't have to be a big site, but you might be applying different in situ technologies. You can try to combine all you need to do is to have a surrogate model that reflects your system behavior. And if you are able to do that with your multiple technologies, then you can run all of these optimization scenario evaluations very easily.
Right. No, that's great. All right, Karen, it's all yours.
Sure, great, thank you. We had a question come in from one of our attendees, I'm not sure who. Are there limits on treatment capacity with higher pumping rates?
Yeah, so I think this is a very good question. So as you increase your pumping rates, you need to ensure that, you know, your system is actually able to sustain that type of pumping rate. So hydraulically, you are able to pump that much water out of the system. So that could be a constraint. In our demonstration case, it was a short-term time frame, and we didn't necessarily observe that type of the response in the system, but we also have a reduced complexity model. So there could be limitations based on how your fate and transport model behaves.
Okay, good, thank you. And again, just everyone, if you have a follow-on question, when you get an answer to your question, please feel free to put it in the chat as well, and we'll cycle back to it. But I'm going to move on to another question from Jarell Yokel. How will you validate your models using field data or lab data? Can you talk about that a bit?
Yeah, that's a very good question. Actually, when we build our model, we are really building model on the shoulder of our contractor, right? They did a fantastic job on build a site model. So what we do is we benchmark our model to their model, but their model is based on, I believe, well data, including monitoring well data and sampling data to do a year-to-year calibration and improvement.
Right, and that speaks to the, you know, robustness of the fate and transport model that you are using and reducing the complexity from. And I think in terms of the validation of the optimization strategies, you know, we provide a tool, pre-screening tool to do a comparative analysis of the scenarios. So the successful scenarios are intended for testing further with the more robust, complete fate and transport models. And there you can see slightly different results perhaps, and the absolute numbers that you can observe, let's say for the mass recovery, would be different, closer to calibrated and validated you know, model results. And so so that one step in terms of validation and going towards more robust approaches for fate and transport models. And also in terms of the strategies success of the optimization strategies, it would be interesting to actually see how these strategies that we identify as potentially successful and that goes into the actual fate and transport models then applied and based on the performance results and evaluations, how it compares back to the original, you know, estimates and how we are the metric of how we are defining success for those strategies.
Yeah, I also want to add that another angle for this question is if there's uncertainty in the model, we can also try to include that during the optimization so that the result become more robust.
Yeah, good point. Thank you, Xuehang.
All right, I will jump to one other question and probably, you know, we end there, or Karen, if you have any others, but it was my understanding that this demonstration was mainly about extraction well optimization, Inci and Xuehang.
Yeah.
So any thoughts about injection wells? You know, injection wells are part of the whole pump and treat system. So what you guys are doing on that direction, and what's the future on you guys thinking on this topic that I think is important?
Yeah, for this application, we are currently only our previous works only focus on the extraction well, but for this year we are start to optimizing the injection well. The key is what we observed is if we only put in extraction well in the central domain, it make the aquifer continuous drawdown, and by putting injection well in the center, it might help us on the battery recovery and even have flushing effects. So which should be able to help us on the cleanup, achieve the cleanup goal.
Yeah, so that's actually in our kind of to-do list that we are working on this year to add some additional capabilities like that to our pre-screening tool.
This was really great. I mean, yeah, it was really, really great seminar. Appreciated your hard work, Inci and Xuehang. And Karen, do you want to switch to the announcement that we have for the next one in line?
Yes, yeah, I will. I don't see any other questions in the chat, so we'll go ahead and do that. Bring up a slide here. Are you seeing my slide now,
Yes,
Nick?
yes,
Okay.
pretty well, yeah.
Well, we appreciate first Inci and Xuehang for your presentation, and that was great. We have another seminar planned now for April 23rd, a couple of months from now, and it'll actually be a nice follow-on to what we've talked about here. The focus in that seminar in April is going to be on optimizing remediation outcomes through the integration of geologic and geophysical data into conceptual site models to support all sorts of decision making. We have some invited speakers, Rick Kramer and Mike Schultz, who are both with Burns and McDonnell, and Judy Robinson, who is one of our colleagues here at PNNL. So we'll be sending out an email announcement with a link to pre-register for that probably in the next week or so. We hope folks will come back and join us.
Well, again, thank you so much for joining. We had a very diverse virtual auditorium today, national and international. So looking forward to other seminars as well for you guys to attend our activities here at RemPlex.
All right. Thank you very much, everybody. Bye-bye.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye.
Bye.